welcome to the next video in our series. In this particular video we're going to have a look at numbers. In maths and science in general we deal with a lot of numbers. I'm sure that you know this. Okay, but in this case we're going to look not at general numbers but at very small and very large numbers. For instance, look at this very small number 0.00421, or else look at this very large number 56, 56 and a lot of zeros. Can you imagine having to write these numbers repeatedly? It would be very easy to make a mistake with all those zeros. So in this case, to help us deal with such numbers, we will look at two systems. The first system is called standard form, and the second system is called prefixes. Both of these are important, not only to manage such large or small numbers, but also to answer questions correctly in your exams. You will need these in other subjects too, so it's good to take note of them. Okay, so throughout this lesson you will need to work some small examples. So pause the video and prepare a pencil and paper before you continue. Okay? First up is standard form. Now there are other ways similar to this of representing numbers that maybe you come across. For instance, there is what is called scientific engineering notations. There's also floating point notation if you are studying computing. Okay, but in our case we will concentrate on standard form because that is the standard for physics. Okay, now look at this example. In standard form, numbers are represented exactly like this in this format. Okay, you have one digit which is before the decimal point, and this digit needs to be between 1 and 9. Okay, any number of digits are then written after the decimal point. We have the multiplication sign and the number 10 to the power of some other number. Okay, so in this case we have 4.24 times 10 to the power of 5. That is our number being represented in standard form. Now look at this example. Why is this wrong? Any ideas? Well, remember what I just told you. In standard form, the number before the decimal point must always be between 1 and 9. It can never be 0. Right? So in this case, the number before the decimal point is 0. And so this is not a correct representation. So be careful, because if you write in questions in the exams where they ask you specifically for standard form, if you write something like this, you'll get it wrong. And what about this? Why is this one wrong? Well, again, in standard form there must only be one number before the decimal point, a number which must be between 1 and 9. Okay, so be careful, because these two are very common mistakes which students make, and usually you end up losing marks, which are really a big pity to lose such easy marks. Okay, now let's have a look at how to convert from an ordinary number to standard form. Okay, and to do this we'll consider the number 4205.2, 4205.2, and we want to convert this into standard form. In this case, we need to shift the decimal point to the left until it is located after the first non-zero digit. This is always your first step. Okay, so here we move the decimal point 3 times. We jump the 5, jump the 0, jump the 2, and we end up behind the 4. We say that we moved 3 hops. Okay, we had 3 hops in this case. So now our decimal point is located behind the number 4, but we cannot leave it like that. I mean, it doesn't make sense just to change the value of a number from 4,000 something to 4. Imagine that was your money. I'm sure you wouldn't enjoy you wouldn't enjoy it. At one time you have 4,000, all of a sudden you would have 4 just because you shifted the point. So that means we need to complete it. We need to complete it with the rest of the syntax, with the rest of the notation. So what do? We include the multiplication sign, the number 10, and then we have to decide the power. Okay, in this case we do the power of 3. Why 3? Because when we move the decimal point jumped 3 places. So the power of the 10 always gives us an indication of how many hops, how many places our decimal point shifts. Okay, and so now it is complete. The number 4205.2 was converted from ordinary form to standard form, and now it is written like this as 4.2052 times 10 to the power of 3. Now let us consider a second example. We have 65,000 as a number. The decimal point is not visible because it is a whole number. But in this case, remember, okay, and we always imagine it to be at the very end. So once again, we shift the decimal point to the left until it is located after the first non-zero digit. In this case, we need to move the decimal point 4 times, 4 hops, right, until it is behind the number 6. So now our decimal point is located behind number 6, and of course, as we said before, we cannot leave it like that, so we have to include the rest of the notation. So we include the multiplication sign and the number 10 to the power of 4 in this case, because we had to do 4 shifts, 4 hops for our decimal point. Okay, note that in this case we don't need to stay writing those extra zeros at the end, because these zeros now are behind the decimal point, so there's no need to stay writing 6.5000 times 10 to the power of 4. There's nothing wrong with it and you won't lose marks, but as such it doesn't look nice because they've got no value behind the decimal point. Alright, so in this case we just write 6.5 times 10 to the power of 4, and that will be our final answer. Okay, so something for you to do. Alright, so now pause the video and try these two numbers on your own first. Convert them from ordinary form to standard form. The first number is 1205.53, 1205.53, and the second number is 400. Okay? Ready? Okay, so let's have a look at what we've done. So in the first case, we needed to shift the decimal point 3 places to the left. And this is what we end up with. 1.20553 times 10 to the power of 3. Right here, I didn't do any rounding. Sometimes when we end up with long numbers, we end up doing some rounding like 2 decimal places, 3 decimal places. Okay, here I wrote the whole number down. Now in the second example, we needed to shift the decimal point 2 places to the left. We had 400, okay, and we end up with something like this, 4.0 times 10 to the power of 2. Now as a convention, try and leave the point 0 in a case such as this. If you write just 4 times 10 to the power of 2, most examiners will still mark it as correct. Alright, it's not considered wrong. However, as a proper notation, you should write it as 4.0 times 10 to the power of 2. So as much as possible, try and write numbers like this in this manner. So what about when we have a small number such as this, 0.000032? Let's do the same procedure and move the decimal point. However, this time we move it to the right until it is behind the first non-zero number, which in this case is the number 3. So in this case, we need to move the decimal point 6 times to the right. Okay, so we have 6 hops. Now our decimal point is behind number 3. Of course, like we said before, we cannot leave it like this, so we have to include the rest of the notation. Okay, and that is the way we write it in standard form. The difference here is, look at the power of 10. The difference between large and small numbers. Since we shifted the decimal point back to the right, the power this time has to be negative. In large numbers the power is positive, while in small numbers the power is negative. Alright, so the answer will be 3.2 times 10 to the power of minus 6. And that will be our final answer. Now try this one out yourself. Convert the number you see over there, 0.000153, from ordinary form to standard form. Pause the video, write down the answer, and then we can check it out together. Ready? Okay, so let's have a look at what we've done. So in this case, we needed to shift the decimal point 4 places back, okay, 4 places to the right, so that will give us 1.53 times 10 to the power of minus 4. So far we've seen how to convert from ordinary numbers to standard form. However, sometimes we may need to do the opposite. Alright, so we need to convert from standard form into ordinary numbers. And how do we do that? Very easy, we just reverse the process that we just did. Okay, let's have a look at some examples now. If we look at the first number, suppose we were given 1.4 times 10 to the power of 3. And we're asked to convert that into ordinary form. So since we have a power of 3, remember that that means 3 hops, 3 jumps. Okay, so we write the number 1.4, and this time we have to do the reverse. So this time we have to go backward. Okay, we have to go backward 3 hops. As you can see, we're going to move the decimal point the other way around, and that will give us the number 1400. Okay, now if we consider the next number, suppose we have 1.4 times 10 to the power of minus 3. This time it's a negative number. Okay, we're keeping the same number so that basically you can appreciate the difference. Over here, the difference is in the power. The previous example was positive, this one is negative. So being a negative, it's going to be a small number. So this time we have to move the decimal point to the left, right? And we have to move it by 3 times. So we've got 3 hops, and we move the decimal point 1, 2, 3. Any extra places, as you can see, we have to fill them in. We have to fill them in with extra zeros. Okay, and that will give us the number 0.0014. Okay, and those were 2 simple examples on how we can convert from standard form back to ordinary form. Okay, so now pause this video and try these 2 numbers on your own. Okay, first convert them from standard form to ordinary form. So the first number here we have 1.2 times 10 to the power of 4. The second number is 4.0 times 10 to the power of minus 2. Try them out. Ready? Let's see what we've done. So in the first case, we had 1.2 times 10 to the power of 4. Now keep in mind, okay, when you look at the powers, immediately you should start realizing, the power of 10 is positive here. I had 10 to the power of 4, positive 4. So you know that this is going to be a large number. Okay, so like this, avoid a mistake where you write a small number instead, okay, because it doesn't make sense. Likewise, the second number is to the power of a negative number, to the power of negative 2. So just by looking at the power, you know that that is meant to be a small number. Okay, so these little things come by practice, it's true, but keep an eye out so that you make sure that what you're doing it well. So again, if we look at the first one, 1.2 times 10 to the power of 4. In this case, we have a power of 4, positive 4, so we're going to shift the decimal point 4 places to the right, and we get the number 12,000. In the second one, we have to shift 2 places to the left, and this will give us the number 0.04. Alright? And that's practically it for standard form. All you need now is just some more practice and you should be fine. Okay? The second system we need to have a look at to help us handle large and small numbers is the use of prefixes. But what is a prefix? First of all, one is a prefix, many are prefixes. So, okay? Well, actually these are things that you have been using for a long time now. And let's look at a simple example. Consider, suppose we are doing some measurements. Okay, suppose we are measuring something and we find that it is 2 centimeters long. The proper unit of measurement here is the meter. But we use the word centimeter. And in fact, centi is an example of a prefix. It is written before the actual unit, hence prefix, pre meaning before, and is used to show us a fraction or a multiple of the unit which is being used. In this case, centi originates from a Latin word centum, meaning 100, and in fact you may find similarities in other languages that you may be studying. For example, cento in Italian or cent in French. Okay? And this means that 1 centimeter is 100 of a meter. In fact, you should already know this from your basic maths, that 1 meter is equal to 100 centimeters, don't you? So let's just have a quick look at how our 2 centimeter example is constructed. Okay? So, the number 2 is the actual value or number or magnitude that we refer to. Okay? And then the letter C represents the prefix, and finally you've got the letter M, in this case representing the unit, which is the meter. Okay? Now there are quite a few prefixes in maths and science. Here we will have a look at some of the most common ones that you may come across. It's important to know the name of the prefix, the symbol and the value. Okay? Now once again, depending on the level of physics that you will be studying, you will meet with more and more of these because there's a whole list of them. Okay? So let's start with the ones which are used for large numbers, because we've got prefixes for large numbers and prefixes for small numbers. But first, we'll start with the large ones. First up is kilo. Kilogram, kilometer. Okay, I'm sure you've heard about this a lot. And the symbol for kilo is the small letter K, which has a value of times 1000, multiplied by 1000. So for instance, 2 kilograms is equal to 2000 grams. Okay? Note the use of the units in the examples. And we will use some different units to get used to them. Don't worry if some of them are still new. You're going to meet them throughout your course, throughout your syllabus. Next, in fact, is the mega. Mega. We've heard about this word mega. It sounds like something big. The symbol is, in fact, the capital letter M, and has a value of times 1 million this time. 1 million. In physics, we will use this a lot in 2 particular areas, although we can use it in any areas, but in 2 particular areas, which are power and energy. You could have also heard it in computing, megabyte. We use it a lot, the word megabyte. Okay? And that's just a simple example. Here we're considering a new unit. You see the capital letter W, which is called watt. It's the unit for power, which we will see later on. And in this example we've got 2 megawatts, which is equal to 2 million watts. The last prefix that we will consider for large numbers is the giga, which is the capital letter G, and this one has a value of 1 billion. In our syllabus, in what we're going to be seeing, this is also used a lot in power and energy, because power and energy gives us very large numbers. Okay, just to serve us as a bit of an example, this time we'll use the unit for energy, which is called a joule, and the symbol is the capital letter J. So if I have 2 gigajoules of energy, that means I have 2 billion joules. And I'm sure you've heard about this also in computing. Even if you're not studying computing, if you go and buy something, right, you've got gigabytes, for example, you buy a hard disk or something which is of a certain size. There are other prefixes for large numbers. For example, after the giga, again something you may heard from your computer is the tera. Okay, and so on and so forth. Now let us consider the prefixes which represent smaller numbers. And once again, pay attention to the symbols which are being used. It is important to write them properly, even capital small letters. Okay? To start off with, we have the centi. The symbol is the small letter C, and this has a value of division by 100. Now, being small numbers, instead of multiplication, we are doing division. So in the case of the centi, we are dividing by 100. And for example, 2 centimeters represents 0.02 meters. Next we have the milli. The symbol is the small letter M. Now milli has a value of division by 1000. For example, 2 millimeters represents 0.002 meters. Okay, because we are dividing by 1000. If we start to go further down the list, next we find the micro. Now this has a somewhat of a strange symbol. In maths and science we meet quite a few different symbols, most of which will be coming from Greek, from the Greek alphabet. For instance, by now you should have already met and you should be very familiar with pi. Okay? Here we have another Greek letter, the letter mu. Mu. Okay, so learn how to write it and how to say it. We say it mu, and it is written in that sort of funny M way. You need to write it like that. Okay, you cannot write it as a small letter M or any other way. That is the proper symbol for mu, which represents micro. And the value of mu is that of a division by 1 million. And as an example, here we will consider time, because we need many things happen in a fraction of a second, so we're talking about a small fraction of a time. Right? So in this case we have 2 microseconds, which would be equal to 0.000002. That's a lot of zeros. And this is why prefixes are important. The last prefix that we will consider is the nano. The symbol is the small letter n. Now nano represents a division by 1 billion. And as an example, we can consider time again. So 1 nanoseconds will be 0. All those zeros 1 second, which would be indeed a very small fraction of time. Right? There are more prefixes in this list. Again, if you keep on studying physics, or you may hear them. Right? You've got, for example, pico, which comes next, and then you've got femto, okay, which keep on representing smaller and smaller numbers. In our case, we'll just stop here, however. As we shall see in various questions along the way, it is important to know about these prefixes and be on the lookout for them, because many times you will need to convert them when working out the numeric questions. Okay, these conversions are important because otherwise your numeric answers will not be correct if you're not careful. But we'll talk more on this when we meet them along our studies. So that's it for this lesson. As a quick recap, in this lesson we talked about numbers, how to represent large and small numbers. First we looked at standard form, and then we looked at the use of prefixes. Okay, so thank you for watching.